Hello everybody, my name is Quindy Lin, and this is my research on the effect of pool size on the dynamics of filamentous structures. So firstly, we need to explain what these filamentous structures are. Cells contain intricate and interconnected networks of protein polymers comprising of cytoskeletons. This structure regulates the internal arrangement and mobility of the organelles, as well as control dynamic changes in cell shape and movement. For example, the stereocilia that are presented in our inner ear, as you can see from figure A. And in figure B, the cilia made of microtubules presented in the unicellular green algae Chlamydomonas. They all are bundle structures made of multiple parallel filaments bounded together. Defects in the formation of the stereocilia in the inner ear can cause hearing loss and balance disorders. Abnormal cilia formation in the Chlamydomonas can disrupt motility. The precise regulation of the size and shape of these filaments is crucial for numerous cellular processes, even as their molecular compounds undergo rapid turnover in a common pool. Now, the question is, how do organelles obtain their specific shapes, and how do cells control their sizes? These filaments are shaped by a collection of associated proteins that regulate filament growth and shrinkage. Here is a schematic of the assembly dynamics of cytoskeleton filaments. As you can see from figure A, filaments are linear polymers composed of individual monomers or building blocks that are added and removed from their ends at particular rates. For example, the rate of assembly is denoted as R and the rate of decay is D, forming a linear structure of length L. In figure B, we see a bundle. Bundles consist of multiple parallel filaments bounded together by binding proteins. In our model, we use 5 filaments. Each filament within the bundle has its own length dynamics, and bundle length is defined as the length of its longest filament. So for my research, we'll be looking at the impact of pool size onto the behaviors of these bundles under steady state conditions. Then we'll analyze and plot the mean length behaviors of filaments and bundles under different pool sizes. I consider these filaments and bundles regulated by a limited pool size, where a finite pool of building blocks provides a straightforward way to regulate the filament lengths. In the system, as the filament grows, the concentration of free units decreases, causing the rate of growth to decline. Thus, the rate of growth depends on the concentration of free subunits. Once the rate of growth matches the rate of decay, a steady state length is achieved. And then finally, we'll be performing some sampling experiments at a specific point in time to analyze and plot the mean behaviors of the bundles under different pool sizes as well. Here is the assembly of 2 filaments in a shared pool, as you can see from the diagram. From graph A, at the start, the filaments will grow in tandem with each other, followed by a slow phase of monomer swapping, which leads to this anti-correlated fluctuation. When one of the filament increases, the other filament would decrease the same amount. This is already intriguing enough, but it gets more interesting once we run multiple trajectories over a long period of time. As you can see from graph B, each curve represents the red filament at a certain point in time. The curve will move until the 2 filaments will reach this anti-correlating fluctuation. As you measure this fluctuation over time, you'll find that the curve starts flattening out, culminating into a final steady state, which is the straight red line as shown. Now, we'll be moving on from just 2 filaments to an entire bundle. To do so, we'll need to keep a few conditions, mainly the inequality. As you can see here, R times N total has to be less than D. R, as said earlier, is the rate of growth, N total is going to be the pool size, and D is going to be the rate of decay. For the study, the decay rate D is going to be at 300, and the growth rate R is going to be at 0.005. And this study mainly consists of 3 different pool sizes, starting with a pool size of 3,500, then 4,500, and finally 5,500 monomers. Here's the graph of one bundle at steady state with a pool size of 5,500. The rest of the graph will be shown in the next slide. Here is the assembly of all the graphs for the single bundle experiments. A few things to point out here is that each bundle consists of 5 filaments, and the bundle length refers to the longest filament in the bundle at that certain point in time. Graph A to C depicts the trajectory of a bundle of equivalent filaments at the specified pool sizes. You could see a greater fluctuation of bundle lengths over time in graph C compared to graph A and B. This is most likely due to the increased amounts of monomers in the pool that the bundle resides in. You can see this fluctuation more apparent in graph D with the probability distribution. As you can see, the blue line, the one with n total of 5,500, depicts a wider range of bundle length values, and it depicts a flatter probability distribution compared to the other pool sizes. Now let's look at graph E. You can see that the blue line takes a bit longer to reach a consistent average value. And in the last graph, graph F, you can also see the blue line having a greater variance value, and it takes a considerable amount of time compared to the other pool sizes to reach a consistent variance value. Here is the assembly of two bundles in a shared pool. One thing to note is that all the data is taken from bundle 1, because that's just how we did it, and also because both the bundles are equivalent, meaning that they both have 5 filaments, their rate of growth, rate of decay are both the same, and there shouldn't be any differences in their behaviors. So looking at the graphs, you can see that I only included one of the trajectory graphs. As the graph with the largest pool size, it had the most fluctuation compared to all the other graphs, which had a lot more overlap, which made it hard to see. But if you look at graph B, the probability distribution, you can see that it is very reminiscent of the one bundle model, with the largest pool size of 5,500, the blue line having the most fluctuation of bundle lengths, and a flatter probability distribution compared to the other pool sizes. Graph C depicts the average length of the two bundles over time. The blue line, the one with the highest pool size of 5,500, has the biggest average bundle length. And graph D is very similar to the one bundle model, with the blue line taking a while to get to a consistent variance and having the highest variance out of the other pool sizes. Overall, this isn't really that surprising of a result, because at the end of the day, we're just adding more filaments into the pool, meaning that all the behavior should just stay consistent. Now let's get to the severing experiments. This is a 2-filament model with severing. As you can see from this graph, one filament was severed at time 1000, which is the black one. After the severing, both the filaments will start growing again, and both will reach a point where they start swapping monomers with each other, which leads to anti-correlated fluctuations. Note that this model does not have the same conditions as the one bundle or the two bundle models, but I wanted to include this because this is what I thought was going to be the behavior we'll be seeing when we are severing two bundles instead of just two filaments. Here is the 2-filament bundle with severing. I have only included the pool size of 5,500 because the other pool sizes would have too much overlap to be able to see the severing. I severed bundle 1 at 3 different time intervals, 140, 180, and 220. You can see 3 clear dips in bundle lengths in both the 2 bundle graph and bundle 1's graph. I also made sure to show the average bundle length. As you can see, it does not have the same behavior as the 2-filament model. The two bundles doesn't seem to be interacting with each other at all. Right after the point of severing, the non-severed bundle did not seem to react with the increased amount of monomers in the pool, and the severed bundle will go right back to how it was behaving previously. A conclusion we could draw from this is that, with the condition we have set for the 2 bundle and 1 bundle models, severing one bundle did not increase the amount of monomers in the pool enough to influence the non-severed bundle to react. Finally, we have reached the conclusion of my research. And there's a few things we could gather from all the experiments I've done so far. One is that bundles under smaller monomer pools were able to reach steady state much quicker than the bigger pools. The other thing is that under the conditions we have set for ourselves, severing one bundle does not impact the second bundle. Now, future plans for this research could have been having more trajectories, since due to hardware limitations, I wasn't able to have as much as I wanted. We could have changed a different condition, like how many filaments is in a bundle. And finally, we should look into the variance and averages for the 2 bundle models as R times N total approaches D. And finally, thank you for Dr. Lashid for giving me this opportunity to do this research. Thank you, Sharik, for helping me out. And a thanks to the College of Science for giving me this opportunity, and the NIH for funding this project. And finally, thank you everybody for listening to my research, and have a wonderful day.